Now, let us look into another problem as a part of which we need to find the inverse Laplace transform of the function log of as plus 1 divided by as minus 1. Please note that the logarithm given here is natural logarithm, that is to the base e. So we need to find f of t, which is inverse Laplace transform of log of as plus 1 divided by as minus 1. We know that Laplace transform of t into f of t is equal to minus d by ds of f of s, where f of t is the function that we need to find out here, and f of s is Laplace transform of the same, which is equal to log of as plus 1 divided by as minus 1. From this we can write that t into f of t is equal to L inverse of minus d by ds of log of as plus 1 minus log of as minus 1. This is because of the reason that log of a by b is equal to log a minus log b. This can further be reduced as minus L inverse of d by ds of log of as plus 1 minus log d by ds of log of as minus 1. This can be further reduced as minus L inverse of a divided by as plus 1 minus a divided by as minus 1. This is further equal to L inverse of 1 by s minus 1 by a minus 1 by s plus 1 by a. We also know that L inverse of 1 by s plus alpha is equal to e power minus alpha t ut. From this we can write that t into f of t is equal to e power t by a minus e power minus t by a u of t. That implies the required function f of t that we need to find out is equal to 1 by t multiplied by e power t by a minus e power minus t by a u of t. So this is the function that we need to find out. Now let us look into another problem as per which there are two functions f1 of t and f2 of t, which are given as u of t minus u of t minus capital T, and f2 of t is equal to delta of t minus delta of t minus 2t. Here we need to find the convolution of f1 of t with f2 of t. We know that Laplace transform of f1 of t is convolved with f2 of t is equal to f1 of s multiplied by f2 of s. As f1 of t is equal to u of t minus u of t minus t, f1 of s is equal to 1 minus e power minus st divided by s. This is because of the reason that Laplace transform of u of t is 1 by s, and Laplace transform of u of t minus t is 1 by s multiplied by e power minus st. From this we can similarly we can write that f2 of s is equal to 1 minus e power minus 2s t. This is because of the reason that Laplace transform of delta of t is equal to 1, and Laplace transform of delta of t minus 2t is equal to e power minus 2st. So from this we can write that f1 of t convolved with f2 of t is equal to L inverse of f1 of s multiplied by f2 of s. This is equal to L inverse of 1 minus e power minus st multiplied by 1 minus e power minus 2st divided by s. This can further be simplified as 1 by s, sorry, L inverse of 1 by s multiplied by 1 minus e power minus st minus e power minus 2st plus e power minus 3st. From this we can write that the inverse Laplace transform is u of t minus u of t minus t, which is inverse Laplace transform of e power minus st divided by s minus u of t minus 2t plus u of t minus 3t. So f1 of t convolved with f2 of t is equal to L inverse of f1 of s multiplied by f2 of s, which is further equal to u of t minus u of t minus t minus u of t minus 2t plus u of t minus 3t. Now let us look into another problem, as a part of which we need to find the inverse Laplace transform of 2 divided by s into s square plus 2s plus 2. Upon splitting 2 by s multiplied by s square plus 2s plus 2 into partial fractions, we get s plus 2 divided by s square plus 2s plus 2 minus 1 by s. So from this we get that L inverse of 2 by s into s square plus 2s plus 2 is equal to L inverse of s plus 1 divided by s square plus 2s plus 2. Please note that we have written s plus 2 as s plus 1 minus 1 by s. This can further be simplified as L inverse of s plus 1 divided by s plus 1 whole square plus 1 plus L inverse of 1 by s plus 1 whole square plus 1 minus L inverse of 1 by s. We know that L inverse of e power minus alpha t cos omega t is equal to s plus alpha divided by s plus alpha whole square plus omega square. Similarly, we know that L inverse of e power, sorry, this is Laplace transform of e power minus alpha t sine omega t is equal to omega divided by s plus alpha whole square plus omega square. So from this we see that in the first term alpha is equal to 1 and omega is equal to 1. So this gets simplified as e power minus t cos t ut, and the second term gets simplified as e power minus t sin t ut. Here alpha is equal to omega is equal to 1, and the third term gets simplified as u of t. So finally we get that e power minus t multiplied by cos t plus sin t minus 1 as a whole multiplied by u of t is the required inverse Laplace transform. Now let us look into another problem, as a part of which it's given that there is a function f of t which is one-sided. It's also given that Laplace transform of t into f of t is equal to a into Laplace transform of f of t. We need to find the f of function f of t which satisfies this condition. or rather say we need to find any function f of t which satisfies this condition if the a is greater than 0. We know that Laplace transform of t into f of t is minus d by ds of f of s, where f of t is the Laplace transform of um, where f of s is the Laplace transform of f of t. So from this we can reduce the given equation as minus d by ds of f of s equal to a into f of s, which can further be simplified as d by ds of f of s plus a into f of s is equal to 0. From the knowledge, we know that the solution of the given differential equation is that f of s is equal to a multiplied by e power minus as, where a is a constant. So from this we can say that f of t is equal to a multiplied by delta of t minus a. So the function of a continuous time function f of t satisfying the given equation is a multiplied by delta of t minus a, where capital A is a constant. Now let us start looking into another problem, as a part of which there is a function v of t given, which is as shown. V of t is a ramp in the period of 0 to capital T, and it has a magnitude of V naught at capital T. We need to find the Laplace transform of V of t. The given function V of t can be written as sum of two continuous time functions, which are as shown in the figure. The first function shown is a ramp, which can be written as V0 by t into t multiplied by u of t, and the second one can be written as minus v0 by t multiplied by capital T multiplied by u of t minus capital T. So from this we see that the given ramp function the given function v of t can be written as sum of the two functions that are highlighted here. So from this v of t is equal to v0 by t multiplied by t into u of t minus t into u of t minus capital T, which is equal to v0 by t into u of t minus t minus capital T multiplied by u of t minus capital T plus t into minus t into u of t minus capital T. So from this we can write that Laplace transform of v of t is equal to v0 by capital T multiplied by 1 by s square minus Laplace transform of t minus t into u of t minus t is equal to 1 by s square multiplied by e power minus st minus t multiplied by Laplace transform of u of t minus t, which is equal to e power minus st. So this is the Laplace transform of given v of t. Now let us start looking into another problem, as a part of which there is a function f of t, which is as shown in the figure. The function f of t is a step function, which is as shown. f of t is 1 in the range of 0 to 1 second, and it is 2 in the range of 1 to 2 second. It is 3 in the range of 2 to 3 second. We can write f of t, here we need to find Laplace transform of f of t. The function f of t in the unit step function form can be written as u of t plus u of t minus 1 plus u of t minus 2 minus 3 into u of t minus 3. The function f of t can be written in the unit step function form as shown. We know that Laplace transform of u of t is 1 by s, and Laplace transform of u of t minus 1 is e power minus s by s. Laplace transform of u of t minus 2 is e power minus 2s by s, and Laplace transform of u of t minus 3 is e power minus 3s by s. From this, we can write that Laplace transform of f of t is equal to 1 by s multiplied by 1 plus e power minus s plus e power minus 2s minus 3 into e power minus 3s. This is the Laplace transform of f of t. Now, let us start looking into another problem, as a part of which the transfer function of a LTI system is given as h of s is equal to s plus 3 divided by s square plus 2s plus 3. It's given that the system is given an input of x of t is equal to sine 3t, for which the output of the system is y of t is equal to a into sine of 3t plus 5. We need to find a and phi. Upon substituting s is equal to j omega in the given transfer function, we get that h of j omega is equal to y of j omega divided by x of j omega is equal to 3 plus j omega divided by 3 minus omega square plus 2j omega. Here it is given that the system is given an input of x of t is equal to sine 3t. So the magnitude of the input ai is equal to 1, and the frequency is equal to s is equal to j3 radians per second. Upon substituting omega is equal to 3, we get h of j3 as 3 plus j3 divided by minus 6 plus j6. This is further equal to 1 plus j divided by 2 into minus 1 plus j. From this we see that the magnitude of the output A is equal to AI multiplied by magnitude of h of j3, which is equal to half, and the phase phi is equal to phase of input I plus phase of h of j3, which is equal to pi by 2. Sorry, which is equal to which is equal to pi by 4 minus 3 pi by 4, which boils down to minus pi by 2. From this we see that the magnitude of the output is half, and the phase of the output is minus 5 by 2. These are the required answers. Now let us start looking into another problem, as a part of which it's given that f of s is equal to Laplace transform of f of t is equal to 2 into s plus 1 divided by s square plus 4s plus 7. we need to find the initial value and final values of f of t. We know that the initial value of a function f of t can be found using initial value theorem, and the condition to be satisfied for the same is the order of the numerator should be less than strictly the order of the denominator, which is satisfied here because the order of the numerator is 1 here and the order of the denominator is 2 here. Order is the highest power of s here. From this, the initial value can be written as limit t tends to 0 f of t is equal to limit s tends to infinity s into f of s, which can be written as limit s tends to infinity 2s square plus s divided by s square plus 4s plus 7, which can further be reduced as limit s tends to infinity. By taking a square common, we get s square multiplied by 2 plus 1 by s divided by s square multiplied by 1 plus 4 by s plus 7 by s square, which becomes 2. So the initial value of given f of t is 2. And also the final value of f of t can be found using final value theorem. For this to be satisfied, the poles of f of s should be strictly on left half of s plane, which is also satisfied here. From this we can see that the final value of the function f of t can be written as limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. This can further be written as limit s tends to 0 2s square plus s divided by s square plus 4s plus 7. So which upon simplification becomes 0. That is upon substituting the value of s as 0. From this we see that the final value of given f of t is 0. Sorry, please note that here final value of theorem can be applied as poles of s into f of s are strictly on the left half of s plane. Now let us look into another problem, as a part of which it's given that there is an input of x of t is equal to e power minus 2t u of t plus delta of t minus 6 applied to a LTI system of impulse response h of t is equal to u of t. We need to find the output y of t of the LTI system. We know that the output y of t of the LTI system is given as x of t convolved with h of t, which is equal to L inverse of x of s multiplied by h of s. We know that x of s is the Laplace transform of x of t, which can be written as 1 by s plus 2 plus e power minus 6s, and h of h is equal to Laplace transform of h of t is equal to 1 by s. So upon substitution and simplification, this becomes L inverse of 1 by s into s plus 2 plus e power minus 6s by s. This can be written as L inverse of 1 by 2s minus 1 by 2 into s plus 2 plus e power minus 6s by s. We got the term 1 by 2s minus 1 by 2 into s plus 2 upon splitting 1 by s into s plus 2 into partial fractions. So this can further be simplified as 1 by 2 multiplied by L inverse of 1 by s minus 1 by 2 multiplied by L inverse of 1 by s plus 2 plus L inverse of e power minus 6s by s. This is equal to 1 by 2 multiplied by u of t minus e power minus 2t u of t, because L inverse of 1 by s is u of t and L inverse of 1 by s plus 2 is e power minus 2t u of t plus u of t minus 6. So the output of the LTI system is half multiplied by u of t minus e power minus 2t u of t plus u of t minus 6. This is the output of the LTI system. It's given that, now let us look into another problem, as a part of which there is a continuous time function f of t which is given as L inverse of 3s plus 1 divided by s cube plus 4s square plus k minus 3 into s. It's given that limit t tends to infinity f of t is equal to 1, in which case we need to find out the value of k. Here we assume that the final value theorem can be applied for finding the value of k. Please note that the condition to apply the final value theorem is the poles of s into f of s should be strictly on LHS of S plane. So we assume that this condition is satisfied. From this, limit t tends to infinity, f of t is equal to limit s tends to 0, s into f of s. This is equal to 1, which upon simplification becomes limit s tends to 0, 3s plus 1 divided by s square plus 4s plus k minus 3. This is equal to 1. Upon substituting s is equal to 0, we get that 1 by k minus 3 is equal to 1. That implies k is equal to 4. So the value of k which satisfies the given condition of limit t tends to infinity f of t is k is equal to 4. Now let us start looking into another problem, as a part of which it's given that two LTI systems of impulse responses h1 of t is equal to e power minus at multiplied by u of t is connected, where a is greater than 0, is connected in cascade with another LTI system of impulse response h2 of t is equal to e power minus at u of t. We need to find the overall response h of t of the cumulative system. We know that the overall impulse response of the cumulative system h of t can be given as h1 of t convolved with h2 of t, which is equal to L inverse of h1 of s multiplied by h2 of s, where h1 of s is Laplace transform of h1 of t and h2 of s is Laplace transform of h2 of t. We know that the Laplace transform of h1 of t, that is h1 of s, is equal to 1 by s plus a, and the Laplace transform of h2 of t is h2 of s is equal to 1 by s plus a. Upon substitution, h of t can be written as L inverse of 1 by s plus a whole square. We know that Laplace transform of t into u of t is equal to 1 by s square. We also know that a Laplace transform of t into e power minus alpha t u of t is equal to 1 by s plus alpha whole square. From this, we can write the overall impulse response of the system as h of t is equal to t into e power minus at into u of t. So this is the overall impulse response of the cascaded system. Now let us start looking into another problem, as a part of which the Laplace transform of a function f of t is given as f of s is equal to omega naught divided by s square plus omega naught square. We need to find the final value of f of t. Please note that here the poles of s into f of s are given as plus or minus j omega naught. For final value theorem to be applied, the poles of s into f of s should be strictly on LHS of S plane. But the poles are on exactly j omega axis because they are plus or minus j omega naught. From this, we see that the final value theorem cannot be applied here. However, upon looking into f of s, we see that f of t is equal to sine of omega naught t u of t. So we see that this is not a converging function and alternates between -1 and 1. From this, we can say that the final value of given final value of f of t corresponding to given f of s can be anywhere between -1 and 1. Now let us start looking into another problem, as a part of which it's given that Laplace transform of a function f of t is equal to s plus 2 divided by s square plus 1, and Laplace transform of g of t is equal to s square plus 1 divided by s plus 3 into s plus 2. We need to find the Laplace transform of integral 0 to t f of tau g of t minus tau d tau. The given Laplace transform can be written as Laplace transform of integral minus infinity to plus infinity f of tau g of t minus tau d tau, because the given Laplace transforms are assuming that the functions f of t and g of t are one-sided. If they are one-sided, the given integral as well be written in the form as shown. So this can further be simplified as Laplace transform of f of t convolved with g of t. So this is further equal to f of s multiplied by g of s. This is by using the properties of Laplace transform. So upon substitution, we get f of s multiplied by g of s as 1 by s plus 3. So this is the Laplace transform of required function. Now let us look into another problem, as a part of which we need to find the convolution result of x of t plus 5 and delta of t minus 7. We know that Laplace, sorry, x of t plus 5 has a Laplace transform of e power minus 5s into x of s, and also delta of t minus 7 has a Laplace transform of e power minus 7s. From this, we can write that Laplace transform of x of t plus 5 convolved with delta of t minus 7 is equal to Laplace transform of x of t plus 5 multiplied by Laplace transform of delta of t minus 7. Sorry, this should be plus 5s. So this is equal to e power 5s into x of s multiplied by e power minus 7s. This is equal to e power minus 2s into x of s. So this is the Laplace transform of the required result. So the required result is equal to x of t plus 5 convolved with delta of t minus 7 is equal to L inverse of e power minus 2s multiplied by x of s. This is equal to x of t minus 2. So this is the required result, which is convolution of x of t plus 5 and delta of t minus 7. Now let us start looking into another problem, as a part of which there is an LTI system which is given an input of 2 into x of t to get an output of 4 into x of t minus 2. We need to find the transfer function h of s of the LTI system. We know that the transfer function of an LTI system h of s is given as the Laplace transform of output divided by the Laplace transform of input. So in the current problem, the Laplace transform of output can be written as 4 into e power minus 2s into x of s, and the Laplace transform of input is given as 2 into x of s. From this, we can write the transfer function of the LTI system as 2 into e power minus 2s. Now let us look into another problem. It's given that there is a linear time invariant causal continuous time system. It has simple pole set s is equal to minus 2 and minus 4. It has simple 0 at minus 1. It is given that there is a unit step input given to the system to get an output of y of t, which has a steady state value of 1. So from this, we need to find the impulse response of the LTI system. From the given data, we can write that the transfer function h of s of the LTI system can be written as k into s plus 1, because there is a 0 at minus 1, divided by s plus 2 into s plus 4, because there are poles at minus 2 and minus 4. But it is given that when there is an input of u of t, the output is y of t. So from this we can write that yu of s, that is the Laplace transform of the unit step response, is given as k into s plus 1 divided by s plus 2 into s plus 4 multiplied by Laplace transform of u of t, which is 1 by s. But the steady state value of the output in this case is 1, that is limit t tends to infinity y of t is equal to limit yu of t is equal to limit s tends to 0 s into yu of s is equal to 1. So which upon simplification becomes k divided by 2 into 4 is equal to 1. That implies k is equal to 8. From this we can write that the transfer function of the LTI system is h of s is equal to 8 into s plus 1 divided by s plus 2 into s plus 4. Upon splitting the same into partial fractions, we get that h of s can be written as shown, that is h of s is equal to a by s plus 2 plus b by s plus 4. So from this, upon simplifying the right hand side term and equating the numerators, we get that 8 into s plus 1 is equal to a into s plus 4 plus b into s plus 2. Upon equating the terms corresponding to s and constant term, we get that a plus b is equal to 8, and 4a plus 2b is equal to 8. That implies 2a plus b is equal to 4. But we know that b is equal to 8 minus a. So upon substituting the same here, we get that a is equal to minus 4 and b is equal to 12. From this, we can write h of s as 12 divided by s plus 4 minus 4 divided by s plus 2. So from this, the impulse response of the LTI system can be written as h of t is equal to L inverse of h of s, which is 12 into e power minus 4t minus 4 into e power minus 2t u of t. So this is the impulse response of the LTI system. Now let us look into another problem, as per which the unit step response of a LTI system is given as t into e power minus tt 2t u of t. Based on this, we need to find the transfer function of the LTI system. So for an input of u of t, the output is y of t is equal to t into e power minus 2t u of t. So as x of t is equal to u of t, x of s is equal to 1 by s. Also we can see that from the given y of t, y of s is equal to 1 by s plus 2 whole square. From this we can write that the transfer function of the LTI system is given as h of s is equal to y of s divided by x of s, which upon simplification becomes s divided by s plus 2 whole square. From this we see that the transfer function from the given information is s divided by s plus 2 whole square.